Hello and welcome to the section 3.1 lecture. Today we're going to start talking about what irrational numbers are and starting to look at decimals. If you've noticed so far, we've kind of lucked out, and everything that we've dealt with have been whole numbers. More specifically, positive and negative whole numbers, which we call the integers. The integers are just one group of numbers that exist in our world. Another group of numbers that we're going to start looking at here are what we call rational numbers. Okay, rational numbers. So rational numbers, or irrational numbers, any number that can be written as a ratio of two integers, a and b, where b is not 0. What does ratio mean? Well, ratio, one way to show a ratio is to use a fraction. So we're really just looking at any number that we can write as a over b, and the only issue that we have is that b cannot be 0. And that these are integers, so these are positive or negative whole numbers. As long as they're both positive or negative whole numbers and b is not 0, it's a rational number, we're good to go. Okay. Here they want you to use a calculator. I encourage you, pause the video, turn these into decimals, and try to turn the decimals into, sorry, words are running away from me, turning the decimals into fractions. If you need a hint on how to do that, the decimal equivalent is, for any fraction, is numerator divided by denominator. So this first one would be 1 divided by 4. Go and pause the video and fill in this table. Okay, hopefully you had a chance to do that. If you're listening to me now with a blank table, you should pause it and do it. Okay, but I'm going to go ahead and fill these in. So we get 0.25, 0.625, 0.6 repeating, 0.2 repeating, and 2.4. Keep in mind that these two repeating decimals are the ones that look like this. They repeat that same number over and over and over again. Okay? Turning decimals into fractions is a little bit harder. Okay? But if you think about, how do I say this number? And not the lazy way of saying it as, well, that's 0.2. That's the lazy way. The proper way to say it is that that's 2/10. Well, saying 2/10 is saying the fraction 2 over 10, which would reduce to 1 over 5. Okay, how do I say this one? I have the tenths place, the hundredths, and the thousandths. So this is 875 1,000ths. And you should reduce that. You can do some work to figure out that that reduces to 7 over 8. But that's just reduction of fractions. Okay. This is, I've looked at this a couple times and I still don't know exactly what they're looking for here, so I'm just going to skip this. But it says, what do you notice about the digits after the decimal point in the decimal forms of the fractions? The only thing that I can really think of is they're trying to get us to say something. I mean, like I said, I couldn't really tell you what it is. I could say maybe it's the first decimal, the first digit. I mean, this is like way up there. Is close, and I use that word kind of loosely, to the numerator times the denominator. But again, that's a stretch. Okay, so looking at that, like, yeah, I mean, like I said, that's kind of a stretch. I'm looking at like this one, 0.22222, and numerator times denominator is 18. So that's kind of close. This one, it actually really works out, 0.66666. 3 times 2 is 6. This one, it's a little bit farther off, but 8 times 5 is 40. And this one, for as small as the decimal is, 4 times 1 is 4. That's kind of close to 2. Like I said, I don't know what they're looking for there. I'm not that worried about it. Okay, a couple reflection questions. I do encourage you to think about these independently before I just go over them, but because they kind of make you think a little bit. This first one, consider the decimal 0.10101000100000, and so on. Okay, so we kind of see what's going on here. We have 10, 100, 1,000, 10,000, 100,000, and this would probably be a million over here. Okay. So do you think that this represents a rational number? Well, we have to remind ourselves, what does rational number mean? Rational number means integer over integer. And all that I saw it give me out of this table is it gave me decimals that ended and then decimals that repeated the same value over and over again. Okay, so like the 6666, okay, or 2222. It didn't give me anything that looked weird, like this looks weird. So I'm going to say no, because there is no repeated pattern. Okay. There's no repeating. Yes, there is a pattern, but it's not that repeating idea. It's not like repeating the same number or same couple numbers over and over again. It always adds a 0 in there. Do you think that the negative sign affects whether or not a number is a rational number? Use -8/5 as an example. So one thing that I do want to talk about with this is when we look at rational numbers, and most of the time that we look at rational numbers that are printed for us, okay, like this one, it looks like this, -8/5. That's definitely equal to, whether I want to think about the negative out in front, or I could think about it as attached to the numerator. Now, technically, it's also the same as 8/5. But this one, even though it's equal, we never want to write that. Okay? We don't want to answer with a negative in our denominator. Since these two are equal, if you ever come across one that looks like this, where it says 8 over a number over a negative, just move the negative to the top or out in front, whichever one you want. Okay, but we never want to write it this way. We can come up with a problem that gets us to this, and then we just take a jump. Hey, let's go to this and answer that way instead. Okay. So we have to ask ourselves, is this a rational number? Just because of that negative there. Well, remember what a rational number is. A rational number is integer over an integer. Is -8 an integer? It is. It's a positive or negative whole number. -8 works. What about 5? Same thing. It's a positive or negative whole number. So the negative sign has no effect. Has no effect. It's still a rational number, and we're good to go. Last reflection question here. It says, do you think a mixed number is a rational number? Well, let's think of a mixed number. How about 1 1/2? Is Seems like a pretty easy mixed number, right? So I've got a whole piece and then another half a piece. Can I write that as an integer over an integer? It's not right now because there's a number out in front. But if you remember dealing with mixed numbers and improper fractions, this is actually the same as 3 over 2. And 3 over 2, 3 is an integer, 2 is an integer. So I think we can pretty safely say that mixed numbers are integers. Sorry, are rational. Okay. Now we've got another idea here. And this is all about writing rational numbers as decimals. And this is a good thing to look at. And there's going to be a little bit of long division inherently that comes up in this. So we're going to have to deal with that. Oh well. Okay. So two things that we saw that gave us rational numbers in the decimal sense. Obviously in the fraction sense, if you can write it as a fraction, it's a rational number. But we want to be able to tell just by looking at the decimal so that we can not have to switch it to a fraction every time or see if it works out. Can I switch it to a fraction? We want to know. Okay? We want to know especially before we try on some very, very ugly ones. Okay? So there are two things that work out to be rational numbers in the decimal world. Terminating decimals, which are decimals that come to an end. 0.25 comes to mind. Okay? That 25, it ends. It doesn't keep going with random stuff. Okay? It's 0.25, period. Another one would be repeating decimals. So decimals that repeat the same digit or even groups of digits. Okay? So things like 1/3. If you turn 1/3 into a decimal, it's 0.33333333333 on forever. But it's repeating that 3. Okay, so we can write it just as 1/3 that's being repeated. There's another cool family of decimals, and that's things like 1/7. Okay, 1/7, if you plug it into a calculator, you might not see it as a repeating decimal, but it is. It's 0.142857. But then your calculator is going to keep going with 1, 4, and it might end somewhere and it might say 143. And it's just rounding up that last decimal. So really what this decimal 1/7 is, 1/7, is this whole thing repeated. So the decimal equivalent to 1/7 is 0.142857, 142857, 142857. And it keeps going. It's really cool that way because it's a really long string of numbers that it repeats out of such an easy fraction. I mean, 1/7. I think it's cool, but I'm weird like that. All right, let's go ahead and look at this next one. It says, write each rational number as a decimal. To do that, we use long division. Okay, you put the numerator under the long division sign and the denominator out in front. That's the important thing, is to remember what goes where. And then if it's not an improper fraction, we're gonna put a decimal and follow that up with a 0. And then we do that whole thing of, can I fit 16 into 5? No. So that puts a 0. Can I fit 16 into 50? Yes, 3 times. Then we multiply. 3 times 16 gives us 48. And then we subtract. 50 minus 48 is 2. Bring down and repeat. Okay, until we get to this 0. And again, that's kind of a hopefully we get to a 0. All right. Let's look at this next one. It says divide 13 by 33. Add a 0 after the decimal point. Subtract 99 from 130. We get 310. And it says to use the grid to help you complete. Yeah. You can stop dividing once you discover a repeating pattern in the quotient, which is the answer. And if we look up here, we notice that it's 0.3939 You could do it again, but if you notice, where is it? Right here. So right here we get this 13. And where has that 13 come up before? Well, it came up all the way up here in the answer, or in the original question. Right? Then we had to look at 0, and so here we would look at 0. And you drop that 0 down. So we would drop that 0 down, and it's 130. And 33 goes into 133 times, so then we'd have a 3. And we should start feeling that repetitive action pretty quickly. And so really this decimal equivalent is 0.39 repeated. I'm glad I talked about that. Write each rational number as a decimal. So here you would want to use division and find your repeating pattern. The problem with this, they sure didn't give you enough room to do that. Okay, I'm going to go ahead and look at one of these. I'm going to look at 4 divided by 7. Does 4 go into 7? No, it doesn't. Does 7 go into 4? No, it doesn't. Does 7 go into 40? Yes, it does. 5 times. Yeah. So it doesn't go into 4. It goes into 40 5 times. Sorry, 6 times. No, 5 times. Jeez. Having a hard time here. 5 times 7 is 35. Subtract. Bring down a 0. This is going to be the bad decision. How many times does 7 go into 50? It goes in 7 times because 7 times 7 is 49. Subtract. Bring down. Wish I had a grid like they had. How many times does 7 go into 10? Once. That's 7. Subtract. See how they didn't give us enough room here? 30. How many times 7 go into 30? 4 times. That's 28. Subtract 2. I still haven't found a repeating pattern yet. How many times 7 go into 20? It goes into it twice. Where 2 times 7 is 14. I actually have to scroll down. This is wonderful. Subtract 6. Put a 0. How many times 7 go into 60? 7 goes into 60 8 times. And that's 56. So 56. And I think I just hit a number that I've already dealt with. Yes, I did. So I hit 40 here. Notice that I dealt with 40 right here. Okay. So remember how I said that 1/7 was 0.142857. Look at what 4/7 is. 0.571428. 571428. And that pattern will repeat just how this pattern repeated. But notice the difference. All I did was started here. 571428. 571428. Anything over 7 is some combination of these 6 numbers in the same order. It's really cool. Like 1/7 starts with the 1. 2/7 starts with the 2. 3/7 starts with the 4. We did 4/7 that started with the 5. 5/7 would start with 7, and 6/7 starts with the 8. So knowing that pattern, and I'm weird. I remember patterns, and so I remember that one. I really like it. But again, that's me being weird. Okay, that's what we get for that one. I'm not going to go over the work on these ones. I'll leave that to you. This is 0.3 repeating. Even though that's repeating, it's a lot easier to find that pattern than it was to find this one. It happens a lot earlier. And then 9/20, I guess, that one we could actually fit here. 20, does 20 go into 9? No, it doesn't. 20 go into 90? Yes, it does. 4 times, that's 80. Subtract, that's 10. 20 doesn't go into 10, but 20 would go into 100. 5 times, so we get 0.45. Okay. Writing mixed numbers as decimals. So here we want to look at the mixed number version. And really, it's just like that other method. It's just like looking at the problems that we just did. The only difference is if they give us a mixed number like 5 and 9/20ths, okay, that would give us 5.45. I don't know why we're using a whole new section for that. You figure out the decimal part and then just put the whole number out in front of it. Okay, so that's exactly what they did here. They found out that 3/4 was 0.75. Added 6 to it because it was 6 3/4, so 6.75. Yvonne made 2 3/4 quarts of punch. Write 2 3/4 as a decimal. They just told us 3/4 was 0.75, so this will be 2.75. Is the decimal equivalent a terminating or repeating decimal? It is a terminating. It ends. Okay, that is a terminating decimal. Yvonne bought a watermelon that weighed 7 1/3 pounds. Write 7 1/3 as a decimal. Well, 1/3, as we found out up top, 1/3 was 0.333 ... 0.333 plus 7 is just going to be 7.3333. That one is a repeating decimal. Okay, we could have written that as 7.3 repeated, and it would have been just fine. Okay? All right, so that'll be it for today. I suppose we need a code word. It's right here. It's right here. I've got my code word. Come on now. Come on now. Watermelon. Watermelon is going to be our code word. Get tired of them always being mathy stuff, so code word. It's right there. Watermelon. Have a good day. We'll see you in class.